All right. Thanks for inviting me to come speak today, and thanks for sticking around for me to give this talk. So I'm going to talk today about what we think is an exciting new technique to expand the capabilities of pressurized rover into kind of the remote sensing regime. So some of the science and the technique I'm going to talk about today is connected to previous speakers looking particularly at infrared spectroscopy, but here we're looking at it at kind of the kilometer scale to try and map out volatile abundances on the surface, as well as also mineralogy and topography at the same time. And I'd like to thank the rest of my team that's shown at the bottom there, based out of Goddard Space Flight Center. Next slide. So this has been covered a little bit by previous speakers, but there's the domain in which the pressurized rover will operate at the lunar South Pole is a good case for active infrared spectroscopy. So infrared spectroscopy, as has been noted, is an extremely useful tool for the study of lunar volatiles as well as mineralogy, also looking at surface weathering and geomorphology. But there have been consistent challenges based on the lighting conditions at the pole to understand what's happening at the surfaces of these permanently shadowed regions and also temporarily shadowed regions. And so we believe that new approaches, new technologies can be brought to bear on this issue to both get at the large science questions about the type and abundance of volatiles at the lunar South Pole, but also to aid the pressurized rover in things like traversal and sampling sites. Next slide, please. So the instrument we're working on here is called TINSIL, which stands for Tunable Mid-Infrared Spectroscopic Imaging LiDAR. It's a little bit of a mouthful. We are being funded currently under a Picasso grant. And TINSIL is essentially a tunable laser imaging spectrometer. So we are using a tunable laser that scans from 1.5 to 3.5 microns. And then we have a single photon sensitive camera that's sensitive across our laser wavelength range. The camera itself can also operate in multiple modes. So it has a 2D mode, which is essentially equivalent to range-gated imaging or snapshot imaging, and then a 3D mode, which gives us a simultaneous range to the target for each pixel, as well as the intensity for that pixel. And below there is just a very simple block diagram of the instrument. The ultimate data output here is going to be essentially a spectral image at each laser wavelength, including a range for each pixel. Next slide, please. So this has been covered a little bit already, but here we're moving our infrared spectroscopy into the active regime, and so what we're doing is shown on the lower left there. We're sending out a short laser pulse on the order of 10 nanoseconds or less. We're then measuring the time of flight between the transmitted laser pulse and the return laser pulse. We're integrating the pulse energy under both the transmitted and received laser pulses. And then we're also obviously measuring the time of flight. And so that's what allows us to measure the absolute reflectance in a zero phase geometry. And, if we measure in between the time of that the laser pulse was emitted and when it was received, that gives us an estimate of the combination of the solar reflectance spectrum, if there is one, and also the thermal emission from the instrument and the surface. And so we can remove that kind of what we would consider background noise, essentially the emission from the surface, which gives us a very high signal to noise ratio in the coldest, darkest places, which are the hardest to measure for passive techniques. And so we think this approach overcomes some of the challenges that have been faced by passive techniques, which include effects of incidence and emission angles. Here, we're always operating at zero phase. Thermal emission from the surface, especially the warm surface, under solar illumination near 3 microns, can have quite an effect on the band depth of the 3-micron water feature. I mentioned the low signal to noise ratio from PSRs. We have kind of the opposite issue where our lowest signal to noise ratio is from highly illuminated surfaces. And then finally, other techniques that have worked this have been targeting short range approaches. Here, we're really extending that range by using a highly collimated source out to kind of the hundreds of meter to kilometer range. Next slide, please. So these are some of the science questions that we plan to tackle with TINSIL. I won't go through all of these in detail. They've been touched on by other speakers, including Deborah. But really, we're interested in understanding the surface hydration across the South Pole, both within PSRs, but also in illuminated surfaces and temporarily shadowed regions. Another nice thing about TINSIL is because we measure that 3-micron feature, we're sensitive to very, very thin layers of surface frost, so things that could actually be affected by exploration activities, potentially including, the use of the airlock on the pressurized rover, also things like landing of some of the robotic landers or the crewed HLS system nearby. So we think this is an important tool that could be used for tracking the exploration effects on the volatile abundance at the South Pole. Next slide, please. Okay, so this is just giving a quick snapshot of how the different modes of TINSIL can be used to tackle various science problems. So kind of the standard mode is when your laser is on and you've scanned across a spectrum, you get an image cube, a hyperspectral image cube. So that's what's shown in the upper left with the volatile mapping. You could think about taking a single pixel and you'll get a spectrum, which looks like the center there. On the upper right here, we're in 3D mode. So we're doing essentially topographic mapping at a single laser wavelength. You can then turn your laser on and you can use your camera as essentially a infrared imager. So here we're going to be monochromatic, but we are sensitive out to 3.5 microns. And then finally in the lower right, that's kind of the single wavelength version where you're just using your laser like a flashlight and illuminating shadowed regions to get context and also potentially learn about geomorphology within those shadowed regions. Next slide, please. I think I've covered most of this already, but these are just kind of some of the benefits of the technology we're bringing to bear. Here, the image sensor that we're starting with under Picasso is a 16 by 16 Mercat APD sensor, but a follow-on effort will probably move up to a larger format, 512 by 512. And one important thing here, as was mentioned with, I think, a previous spectral imager, here we can choose our wavelengths in kind of what you could consider random access fashion. So you don't necessarily need to take a whole spectrum every time. You can choose, 4 or 5 wavelengths and get what we call reconnaissance spectra. Essentially, are you looking for, a clear evidence of a hydration band or a water ice band before you take the time to do a more precise spectrum. Next slide, please. So this is just a little bit about our laser approach. So we use a tunable OPO where we pump a lithium niobate crystal with a 1-micron microchip laser. We then have 2 output wavelengths. One, which we call the signal, is the lower wavelength. The idler is the higher wavelength. Those 2 energies sum to the photon energy of the pump. And based on how you design your crystal and how you code it, you can change essentially the wavelength ranges of your signal and idler. On the right there, bottom right, is a plot of the crystal design for our TINSIL system. So here we're targeting kind of 3.5 to kind of 1.5 to 3.5 microns. The crystal will let you go higher in wavelength. We stopped at 3.5 because essentially as you move further into the infrared, your thermal noise starts to go up and up. And so we think that's a good stopping point for getting organics and obviously water and hydration. We do have ideas about how we can potentially extend it out to a little past 4 microns to try and get hydrogen sulfide and a strong CO2 absorption. Next slide. And then the camera portion, this is a Mercad APD camera. You can see in the upper right is the spectral response of the camera, so it's relatively flat over our wavelength range. It actually does go out to about 4.3 microns, but as I said, we kind of do our filtering out to 3.5. The basic concept is that you fire a laser pulse, you open a shutter, which again, this is a really narrow shutter, it's 100 nanoseconds or so. So within that gate time, our laser pulse is much, much brighter than the background. Then you time tag the return of your laser pulse within the gate, and then you also know the gate delay, and so you know your time of flight. And then you can integrate your signal during the gate to measure the return pulse energy, combine that with your range and your transmitted pulse energy, and you've got your zero phase reflectance. And one key aspect here is we're really trying to push TINSIL to be kind of the most photon effective, efficient system possible. So we're using monochromatic illumination and we're measuring every photon we get back. So we have sub single photon noise equivalency over a frame. So we are doing photon counting within our camera. Next slide, please. Okay, so this is just a brief slide covering the instrument parameters as well as our predicted performance, which kind of hits that kind of 1 kilometer at a 50 millisecond averaging time. And then within a cold surface, for a warmer sunlit surface at the pole, our range decreases to kind of about the 25 to 30 meter range to keep the signal to noise ratio of 150, which is what we target for a getting to the background hydration level. Next slide. And I think this is my last one. This just kind of covers some thoughts on the concept of operations for TINSIL with the pressurized rover. There are a lot of different types of experiments we can foresee, including, topographic mapping at the centimeter scale. Volatile mapping is obviously the key one here, but also doing things like finding regions of interest for follow-up sampling by astronauts, mapping out surface frost for ISRU efforts, and also using the topographic mapping to help plan traverses out to kind of the kilometer range. And that's it. Thank you.